with basically what we consider nanometer-sized tools with precise dimensions, we're interested in probing different biological systems. So we start simply, and I'm going to go through a little bit of discussions first at the cellular level, and then I'll get to the systemic level. So this is a macrophage taking up particles of different size. And I showed an image here of a hex nut, obviously an unusual-looking object, but clearly a man-made particle. And we watched the different internalization processes as the particles enter the cell, the different endocytotic processes, macropinocytosis, clathrin-mediated endocytosis, for example. We watch the internalization process. We use electron microscopy to watch where they're located in the cell, how they traffic within the cell as a function of size and shape. We measure the kinetics of uptake using flow cytometry and looking at that as a function of size and shape. And it's actually these particles here that are in our library of particles are the particles that are able to get internalized into cells, into non-phagocytic cells, the fastest over any other shape in our current library of particles. And they're not the smallest particles we have. And so there's something about the physics of this asymmetry, and it's actually very close in symmetry to many rod-like bacteria, and we're interested in the physics of that. And so that's beginning to understand some of the shape characteristics. We begin looking at how the particles are internalized and how they're trafficked. When you start having particles that have a fenestration or a hole in the center, what type of endosomal compartment does that initially form? How do those endosomes evolve into lysosomes, or what's unique? What's the pH environment within those endosomes as a function of time? And we begin looking at the details of these types of structures. We look as a function of time here, and this is a clathrin-coated pit, and we can see typically the dogma was that the particles had to be smaller than the diameter of the pit in order to go internalized, but actually we see the remnants of clathrin-coated pits on particles that are 200 nanometers. And we can start doing competition experiments with different types of inhibitors to start deducing the range of mechanisms by which cells internalize these particles. And so we're beginning to deduce that, and now we're interested in some of these intracellular trafficking as a function of size and shape. Obviously, size and shape is just one piece of the puzzle. The charge, or the zeta potential on the particles, plays an enormous role. What we find in non-phagocytic cells, particles that have a positive charge on them are attracted electrostatically to negatively charged cells, and you can easily get internalization of a wide range of particles, even up to microns in scale, that can get internalized into non-phagocytic cells. When you drop the zeta potential to the negative range, where everything else is constant, you can dramatically inhibit the uptake of particles. And so our strategy is, can we now, with this observation, keep particles with a negative charge and now override that negative charge with specific targeting ligands to do specific targeting and try to get the specificity associated with that. And this turns out to be a really powerful combination. We keep particles with a negative charge, and then we can start decorating them with different types of biological molecules or non-biological molecules on the surface to begin looking at targeting. And we try to do this in a careful way where we had different ligand classes. We would have a targeting ligand, and we would have controls that might be a peptide versus a scrambled peptide, or an antibody versus a isotype control. And I just want to show you some glimpse of this data. This is an example of transferrin targeting. As you know, transferrin receptor is overexpressed on a wide range of different cancer cells. This is an antibody, OKT9, that we conjugate onto the surface of these well-defined particles that have a negative charge. In HeLa cells, we have terrific uptake at very low particle concentrations. This is a multivalent particle with lots of these ligands on the surface. But relative to its isotype control, just IgG on the surface, we have less than 5% uptake. So we have really a huge window of specificity with this parameter of negatively charged particles with targeting ligands. This is 4-hour uptake and dosing, and then this is 72-hour tox. So this particle is not designed to have a cytotoxin in it. This was just a targeting study. And so we actually look at this as a sort of a plug-and-play approach that we could put different cargoes in with different targeting ligands and begin spelling these different approaches out. There's a range of different cancer cell lines that we've looked at that all overexpress the transferrin receptor to different degrees. Shown in red here is the uptake versus the green, almost in a baseline here. And this almost tracks with the degree of overexpression of the transferrin receptor on a whole host of these different cancer cell lines. So we're beginning to start moving into various therapeutic approaches. This is Herceptin conjugated onto these particles. When I talk about 0% Herceptin, that's 100% IgG. So we're varying the amount of Herceptin antibody versus an isotype control and just varying the stoichiometry or ratio of these two. When you have no Herceptin, it's 100% IgG. You have the same story, very low uptake. And as you systematically increase the amount of Herceptin, you can get very good uptake. And this is a negative control cell line. It's negative for HER2 expression. So this is really effective at surface chemistry, and I just want to show you how we're using this very simple system and trying to move this into the clinic. So this is actually a commercial product that our company Liquidia is moving into the clinic in September for a very simple system. These are PLGA, lactic acid glycolic acid copolymer, particles that are these 80 by 320 nanometer particles that we can sterilize by filtration. We can combine them with just about any antigen, and we have a tremendous enhancement of the antigen associated with our particles. And so we're entering a clinical trial in the third quarter of this year, and we're moving into a variety of different other approaches. And it's a simple delivery system, and we're beginning to add different types of immunostimulatory molecules as cargoes to combine antigens with autostimulation. Other types of vaccines that we're working on are the so-called conjugate vaccines, which are combinations of polysaccharides and proteins. You think about pneumonia for a Prevnar. It's a $4 billion a year vaccine. That's a molecule that's designed by covalently attaching 13 different polysaccharides onto a protein, and it's designed the way an organic chemist would design them. And I'm an organic chemist, so I'll slam organic chemists. But it's a very complex synthesis to conjugate polysaccharides onto proteins. Using print, we can simply mix these polysaccharides at whatever ratio we want. We can cross-link the protein matrix. We're able to process these at just above room temperature. And we have tremendously effective vaccines where we can compare the performance versus Prevnar. These are the print-based conjugate systems. Each one of these points is an animal in the response. And you can see the print analogs are coming all out of the gate relative to Prevnar, and then we do a post-boost, and we have really great performance. So this is a powerful tool to begin systematically combining different types of molecules in a matrix. So that's all cellular-based approaches and some in vivo work with the vaccines intramuscular. What happens when we start varying size and shape and deformability for parenterally delivered particles? Where do they go? What role does size, shape, surface chemistry play? And we now have this toolbox to begin looking at that. We use different types of imaging beacons on the particles. This is copper 64, so we can do quantitative micropet CT imaging. And this is a fluorophore that we have on the particles. And I want to show you one story where we got some pretty well-developed data associated with this. And this is a story that's inspired by red blood cells and cancer cells. Red blood cells are very deformable when they're young. In humans, they're 8 microns in diameter. In mice, they're 6 microns. They're able to squeeze through 3-micron-sized pores in the sinusoids of the spleen. They can undergo 100% strain and squeeze through these different types of pores. When red blood cells get older, they get stiff, like many of us do when we get older, and they can't squeeze through these pores. And that's how the body will remove old red blood cells from young red blood cells. Subra Suresh here at MIT has been looking at the deformability of cells for many years, and he's wrote one of the most definitive papers out there. And what's known as cancer cells, in fact, have an order of magnitude more deformability than their healthy cell analogs due to disruption of the cytoskeleton. And in fact, metastatic cancer cells are yet even more deformable than regular cancer cells. And this is a thought that people believe from a mechano-biology point of view is how these cells get into places they normally don't belong due to the deformability. So people have measured the deformability and modulus of these cells, And as a material scientist, we can systematically replicate modulus and begin looking at the effect in a rigorous way of the deformability and biodistribution. So here's an example of cells, red blood cell mimics that we make using print. This is a hydrogel made out of polyethylene glycol. We can vary the modulus by controlling the cross-link density. We put a red dye in there to guide your thinking that they actually look like red blood cells. And we think these are opportunities for actually loading them up with different biologics and different types of molecules that we want to deliver. This is a microfluidic channel, a 3-micron channel with 6-micron particles, because we're going to be working in mice. And you can see the particles going through these channels and actually deforming and squeezing through. And in fact, we can do time-lapse photography, quantify the extent of extension and the amount of strain that these particles undergo. We can vary the gap and look at the viscoelastic recovery as they come through these channels and reform. When the particles are stiff, they get clogged, so we can vary the degree of deformability. We can begin doing in vivo experiments. So this is a tail vein injection of these particles. We use an intravital microscope sitting on the capillaries of the ear, and we can begin watching the flow of our particles through the capillaries. The story is, when the particles are soft, they're extremely well tolerated. These are 6-micron sized particles. When they're hard, the mice are highly distressed. There's pulmonary emboli, and we have to sack the animals. And so this is a very straightforward way to begin looking at deformability. We get hundreds of data points from the intravital microscopy, so we can fit the data very well. This is a 2-compartment fit. 350 data points allows us to back out elimination half-lives and distribution half-lives as we vary the modulus here. And when we start getting into the deformability of a red blood cell, which is about 20 kilopascals, we start seeing a tremendous increase in our circulation times. We're starting getting elimination half-lives are getting into several days now. And they're quickly eliminated when they're stiff due to the pulmonary emboli. We can look at the lung tissue. This is when the particles are stiff. In red are our particles. We can see they're hung up in the lungs. And when they're soft, they go right through. And you can see the organ distribution changes dramatically. We start seeing the lung distribution at a certain modulus break, and then we start seeing accumulation in the spleen. And we see a persistent extended circulation in blood. But what's interesting is for these large particles, we see a very low liver uptake. And so we're interested in the implications and opportunities associated with particles that can do that. So a lot of that was done at 2 hours, and now we're going out to 5 days, and this is out to 5 days, and we see our particles staying in the spleen as a reservoir and continuing to circulate. They're not cleared by macrophages. They're sort of held up in the spleen, and we're now getting into these very long half-lives in these systems, and we're interested in these as long circulating particles.